Okay, we're now recording Mikhail's talk. Okay, over to you, Mikhail.
Thank you. Thank you. So let me start.
Yeah.
It's a pleasure to visit and give a talk on Rogers and Lewis examiner. And so this is the talk. So I'm going to talk about form evaluation. I gave similar talk before, so it might be deja vu for some of you. And the talk is I don't know, there's kind of some noise. I don't know if it's you want to mute or not.
We can't hear what you're saying, Mikhail.
Yeah, I'm saying that yeah, there's some noise. I don't know if you want to mute or not. If you want to mute to reduce the noise, I hear some noise. But so let's talk about form. Not everyone is muted. Maybe that's fine. I can hear it. I can hear some noise.
Just the participant Semi-Hoslam is not muted. I think that's where the problem is. Roger, you should be able to mute people as the host.
Okay, great. So let us continue. So we're going to talk about forms. And so forms are the combinatorial CW complexes with some decorations, maybe of some local type, embedded in R3. And they appear over time when we build link homology. So for link homology, forms are extremely useful. And I'll tell you about a version of these forms and some particular evaluation of forms that can be used for SL3 homology, and then also for some more mysterious extension of this homology to planar graphs. And so let us start. So we have a closed form F in the free space. So what does it mean? It's a two-dimensional CW complex with generic singularities. And what do we mean by generic singularities? We allow points of three types, so regular points, which have neighborhoods homeomorphic to a disk. And points along the seams. A point along the seam has a neighborhood homeomorphic to the product of a tripod of this graph with three edges and an interval. So it's tripod times an interval. So think of these points as sort of constituting seams of a form. And finally, we have vertices. We allow vertices, and vertices points where four seams meet. So at the vertex, there are six corners. Six corners, one for every pair of seams. So one way to think about the neighborhood of the vertex is it's homeomorphic to a cone over a complete graph on four vertices. So take four vertices, just draw this complete graph. You can draw it as a graph on the surface of a Q-sphere and take a suspension. Take the cone over it, and that's what standard neighborhood of the vertex look like as such a cone. So these are, in fact, if you have an arbitrary combinatorial two-dimensional CW complex, you can deform it up to homotopy equivalence or simple homotopy equivalence so that it locally looks like this. So from the homotopy viewpoint, this is generic. Everything can be deformed to that type. And here, so given such an F, we denote S of F, the union of single points of F. So these are, so what are single points? So these are the union of points on seams and single vertices. So just take union of those. So that's SF. That's one-dimensional. Yeah, it's one-dimensional. You can think of it as a four-valent graph. This graph sits in R3 because form sits in R3. So form comes with an embedding to R3. And the graph might contain loops. Actually, this is a picture. This is an example of a form which has a singular seam, which is in fact a loop. It closes onto itself. So this is S of F. It's such four-valent graph plus possible loops. So examples of forms. So any surface embedded in 3 space is a form with empty S of F, no singular points. Another example: take a Q-sphere and add equatorial disk. Then that's a form with singular singular graph, the circle, no vertices. And if we remove, given a form f, if we remove single graph of f from a form, we have a union of open facets. So open facets, so f minus s of f is a surface, and its connected components are called facets. So for instance, this form has 3 facets. So in this picture, top, middle, and bottom. This one has single facet. And finally, an example of a form with a singular vertex. And to build that form, we start with 2 torus. Start with 2 torus and add a meridional disk. So inside the 2 torus, and add another disk, longitudinal disk, on the other side. Because when you talk about inside the other side, we mean that it's embedded in R3, which will come in handy. So for this form, the singular graph consists of the singular vertex and 2 singular edges. So this is what singular set looks like. And just variation on this example would be take 2 torus. Take a 2 torus and add some number n of parallel disks along the meridian. Louis, please.
Above, you wrote 3 facets were all disks for the theta foam, but not all facets are disks.
Yeah, so for this form, all facets are disks.
Right, but in general, not all facets are disks.
Yes, and in fact, you can always add genus to a facet. You can always just add disk to a facet. And this is just an example where you can have many singular vertices by putting m parallel disks on one side of the 2 torus and m parallel disks on the other side of the 2 torus. And it could be very complicated, of course. So we're gonna do is convert from topological information to algebraic information in a moment, and it's a particular example of this evaluation where to forms we assign polynomial expressions. These are interesting evaluations. They started, I think, in depth from the paper of Robert and Wagner 3 years ago, in which it's for SLN, it's much more subtle. I'll tell you about the SL3 case, where you also don't need to orient facets. And so there are pros and cons. So the con is that the characteristic is skewed, but there are more choices of forms. So let me tell you, I'll give you an example of such a map. And we're going to work in characteristic 2, which simplifies definitions. So there are no signs. You can ignore possible signs. Someone says they can't hear either. So let me check. So my volume is close to max. I'm not sure. So my volume on my laptop is close to max. Can you hear me?
Well, I can hear you perfectly.
I could hear you.
It may be that the person who can't hear it needs to turn up their volume. I don't know.
It's a bit distorted, Mikhail's channel. I can understand him just about.
Yeah,
It is distorted. It's in a lower tone and sounds normal.
Yeah, I think it's okay.
All right. Well, let's try to continue. So we work in characteristic 2. Well, this is our ground field F2. So we're going to, to a form, we're going to assign a polynomial with coefficients in k in 3 variables, x1, x2, x3, and this polynomial is going to be symmetric. So in fact, the form will give us a symmetric polynomial. So it's a polynomial in elementary, which we can write as polynomial in elementary symmetric functions E1, E2, E3 in the axis. So to define this evaluation, this invariant, we introduce the notion of admissible coloring C of the form. And admissible coloring is a map from the set of facets of the form to numbers 1 to 3. So to a facet, we assign a number such that along any seam, the three facets have different numbers, so 1, 2, and 3 in some order. In particular, this means that the three facets must be different. So it's easy to come up with a form which comes from two directions to a seam. Well, such form has no admissible colorings. So an admissible coloring is such an assignment to facets of the form. Colors 1 to 3, such that along each singular edge, the colors are distinct. And also will allow additional decorations of forms that are kind of like observables. Think of them as in the physical language, they're going to be called observables, and just going to allow dots floating in the facets. The dot is like a point that can float in the facet, but not jump across a seam to another facet. And if you have many dots on a facet, we can collect them into a single dot labeled n, the number of dots. And so given the coloring C of this form, define Fij of C. And Fij of C is the union, it's a union of facets colored I and J. So it's F12 of C will contain this facet and this facet, but not the facet labeled P. So we take this Fij of C, and there's an interesting observation that Fij of C, so in general, it's, if I sort of, here it should be, it should be 3. Fij of C is a closed surface in R3. So let me just look at the case F12 of C. Why is that a surface? Well, it's a surface at each radial point inside the facet for a point on a singular edge. F12 keeps only 2 facets out of 3 adjacent to the edge, so it's a surface locally in the neighborhood of this point of this surface. So finally, we look at singular vertices. So let me just let's say that the coloring has 1 for this corner and 2 for this corner. Then this corner is adjacent to both 1 and 2, so it must carry label 3. Now this facet is adjacent to both 1 and 2. It also must carry label 3, and so on. So this one is adjacent to 2 and 3, so it must carry number 1. And finally, the bottom one is next to both 1 and 3, so it has to have label 2. So you see it's full symmetry. So the coloring of any facet matches the color of the opposite facet. So 1, 1, 2, 2, and 3, 3. So if you draw the link of the vertex, then up to symmetry, there's only one coloring of the thing. So 1, 1, 2, 2, 3, 3. And now if you take any two colors, say 1 and 2, then we see a cycle inside the graph. And then the neighborhood of the surface F12 of C for that point is going to be homeomorphic to the cone over that cycle, so to the 2 disks. So it's near the surface. So if you, for instance, here, if you take union of facets 1 and 2, you see it's a surface in the neighborhood of this point. And we obtain this observation that Fij of C is a closed surface in this case. And in particular, because there are no boundaries, so our forms are closed. So surfaces are closed, so there are no boundaries. So it's a closed surface. And everything is combinatorial. And so in particular, it's orientable, and it has even Euler characteristic. With this observation, we're going to assign to the coloring C the following expression. It's going to be a rational function with possible denominators xi plus xj. Where first we look at,
Excuse me, is it easy to see that it's orientable?
yeah, because it's a closed, everything is combinatorial. It's a closed surface embedded in R3.
Oh, okay, sure. Okay.
So now let's assign a rational function in x1, x2, x3, three variables, one for each color, two coloring C of the form F. So first we recall that facets may carry dots. So we just look at the number of dots on facets of each color, denoted by di. So di of C is the number of dots, total number of dots on facets colored I, or I1, 2, 3. So we just put this as a numerator, x1 to the d1, x2 to the d2, x3 to the d3. And then for each pair I less than j of colors, so 1, 2, 1, 3 to 3, we look at the surface Fij of C. It's orientable because even for the characteristics, this number is an integer, chi of Fij divided by 2. So we put in the denominator xi plus xj to this exponent, an integer. So
Isso.
this might be either positive or negative. It's
O
nice.
que é que se lembra
Very
disso?
young,
Ah.
very young participants. And,
E foi agora buscá-lo. Ah, boa.
Could everyone except the speaker mute, please, until they need to say something?
well, it's good to know that even the youngest ones are listening. So right. So these are integers. We can take xi plus xj to that exponent. We put this in the denominator, but it really depends on Fij because sometimes chi is negative, sometimes it's positive. So it could end up in both numerator or denominator eventually. But sometimes it's indeed in the denominator. And then we define the evaluation of the form F to be the sum of these evaluations over all colorings, over all admissible colorings of the form. And we'll look at examples right away. But the first interesting result is that as we sum, individual terms may have denominators of this form, but the sum is always a polynomial, and in fact, a symmetric polynomial in x1, x2, x3. That's one of the interesting facts. The evaluation is a polynomial as we sum over all colorings. So let us look at some examples. Let us take a two-sphere with n dots. Well, there are three possible colorings of the sphere by colors 1, 2, and 3. So let us look at coloring C1 by color 1. So what is the data for this case? So this is the formula. So we need to look at the surfaces Fij of C. So F12 of C is the union. It's the union of facets colored 1 or 2. In this case, everything is colored 1. So F12 of C1 is the entire two-sphere. F13, union of facets colored 1 or 3, and that's also the entire two-sphere. And F23 is union of facets colored 2 or 3. There's nothing, so it's the empty surface. We compute their Euler characteristics divided by 2, 1, 1, 0. And this is what enters the denominator. You see x1 plus x2 appears with this exponent. x1 plus x3 has this exponent. We have n dots on a facet colored 1, so it's x1 to the n in the numerator. So the evaluation of the form F of this coloring C1 is this expression. And now to define the entire evaluation, we need to take the sum of these terms for all three colorings. This is a very simple example with additional symmetry. So for the color by 2, you should just rotate colors 1 to 3. For coloring 3, likewise change, kind of rotate colors 1 to 3. So you just need to take this term, this expression, and add 2 more expressions where we cyclically rotate the colors 1, 2, and 3, indices 1, 2, and 3 for them. You get some rational expression. You can check if things cancel out. And in fact, it's going to be, if you add it up and cancel whatever's possible, you end up with a complete symmetric function in x1, x2, x3 in degree n minus 2. Degree is n minus 2 because numerator has degree n, denominator has degree 2. It ends up being a polynomial, so it has this degree n minus 2. But it's a complete symmetric function, so in this case, it's a sum of all possible monomials xi to x1 to some power, x2 to some power, x3 to some power. And in particular, it's a polynomial. And let me give you, so for instance, if there are no dots, that's 0. If there is one dot, it's 0. If there are two dots, well, that's h, that would be h0, that's 1. And 3 dots will give us x1 plus x2 plus x3. And here is another example. And this example is called what we call a theta form. Theta form. It has it's a two-sphere with an added equatorial disk. Has 3 facets. Let us put N1, N2, and 3 dots on those facets. And look at possible colorings. So there are 6 possible colorings because we can color top facet by one of the 3 colors. And for the next facet, there are 2 colors left and 1 facet for the remaining colors. So there are 6 colorings. You can parameterize them by elements of the symmetric group S3. If you say that this is facet 1, 2, and 3, then we can assign color sigma of 1 to the top facet, color sigma of 2 to the middle facet, color sigma of 3 to the bottom facet, where sigma is any permutation of 3. So it's just a way to label, to enumerate all the colorings. So for the coloring given by sigma, what's the evaluation? Here I should put f comma, yes, so for a given sigma, we claim that this is the evaluation. So f sigma is this term. So why is that? So what are the surfaces? What are the surfaces? Fij sigma. In this example, every color there's going to be one disk of each color for colors 1, 2, and 3. So when you take Fij, there's always a union of 2 disks, one for color I, one for color J. So it's always a two-sphere, and its characteristic is Q, so it enters with exponent 1 into the expression. So each Fij for each coloring will carry exponent 1. So it means that we'll just have one Fi plus Fj, sorry, one Xi plus Fj for each pair Ij. And as a result, the denominator is always the same. It's this one. And the numerator depends because the number of dots may be different, and 1 and 2 and 3. So the numerator, I should put here, so there's a, I think I should, instead of this, I should say x. Instead of this, I should say x, x1 to the n of sigma 1, x2. Let me do it differently. Let me just put here n1, and I'm going to put here sigma 1, x, and q. Okay. So the exponents are n1, n2, and 3, but the indices change with the permutation. Now, if you look at this expression, and that's for a given coloring, that's for a given C, that also depends on sigma, so C of sigma. And now we sum over 6 terms over all sigma in S3. Now you recognize this as the characteristic version of the sure function in the while character formula. For the sure function, the formula is very similar. You have a product of xi minus j in the denominator, while in characteristic 2, plus is equal to minus. So we can also write this as xi minus j. And there are some signs here given by blank for the permutation. And otherwise, it's just that formula. So this is similar to the while character formula. And in fact, the ratio is a polynomial, and it's the sure function as lambda for the partition lambda given as follows. Let us order in 1 and 2 and 3, and we decrease in order, non-increasing order. So take n1 minus 2 and 2 minus 1 and 3. This is our partition. So then this is the expression for the sure function. I mean, I can add the mod to it. This is the expression for the sure function for that partition. Now, if it's not a partition, if, for instance, n1 is equal to 2, right? If n1 is equal to n2, then the whole thing elongates to 0. So, for example, if n1 is 2, then this f elongates to 0. So, otherwise, if everything is good, we get the sure function, or otherwise 0. So it's interesting to see the sure functions of the fundamental in representation theory come out of form evaluation for the simplest forms. Maybe pause for questions. Okay, so let us move on to building state spaces from this evaluation, because for now we have numbers to closed or polynomials to closed form. We can assign a symmetric function. Now here, what we can do, and it's an example of so-called universal construction. Whenever we have a number or element of a commutative ring assigned to a closed object of dimension n, like a manifold or a form, then you can build a vector space assigned to cross-section to an object in one dimension less. So what you do, given an object in one dimension less, you can look at all the n-dimensional objects with that boundary and take the linear combinations. And on the space of linear combinations, you can build them by linear form. Just take two such objects and glue them together to get a closed object, and then apply your function, apply your evaluation to get a number. So this gives you a bilinear form on the vector space with the basis all possible n-dimensional objects with a given boundary. And you can take the quotient, you can take mod out by the kernel of this form. And sometimes that's interesting. So let's see how it works in this case. If you take a form and you take a generic cross-section, a generic plane, in the cross-section we see a trivalent graph in the plane. So this is one example. So take a cross-section, we see a trivalent graph because singular seams we have three facets coming in. So cross-section will give us a singular, will give us a three-valent vertex. So let us define a free module. So given a graph gamma in the plane, trivalent, so we can build we can define a free module, free of gamma, as follows. Look at all the forms f in lower half space with boundary of f equal gamma. So gamma is fixed, f is variable, all forms with a given boundary. Let us introduce a pairing on this very large R module. Everything is over R. You have some ground on everything R. We define a pairing on this vector space. So specifically given two forms F with boundary gamma forms F1, F2, we can reflect one of them and glue with F2 to get a closed form. So this is a closed form. So we can apply our evaluation to get an element of the ground ring of symmetric functions. So we write it like this. We combine F2 and its reflection of F1 into a closed form, evaluate to get an element of R. And this extends by linearity to pairing. In fact, it's symmetric pairing on this very large 3R module with the basis of all forms with boundary gamma. And now define the state space of graph gamma as the quotient of this large vector space by the kernel by the uniform. Now, what does it mean? So we say that the linear combination of forms the phi with boundary gamma when the i's are coefficients, this sum is 0 if for any form f with the same boundary, if we take each fi and we glue it to f, so reflect f, we glue it to phi, evaluate, that's an element of R, times lambda I, which is an element of R. So we have this expression in this equality in R. This is the definition, what it means for the sum to be 0 in the quotient in the state space. If no matter what we attach at the top, we get 0. And this is an example of universal construction, where you can start with any invariant of closed and dimensional objects. This could be forms, this could be manifolds with decoration, whatever you want. And the same procedure will give you state spaces for objects in one dimension less using this construction. So this is completely general. If you look at my slides from other lectures or look at our lectures of my recent papers, there's going to be lots of references to other examples of this construction. I recommend you, there's work of Friedman, Walker, Wang, other people, Caligari, Friedman, Walker, where they look at the more general case where you don't propose any relations whatsoever on the invariants of closed manifolds. There are many other examples. You get something which is similar to a TQFT, but not quite TQFT. It doesn't satisfy the idea axiom for the disjoint union, the state space for the tensor plot, for the state space for gamma 1 union gamma 2 is not isomorphic to the state space of gamma 1 tensor, state space of gamma 2. There's only an inclusion, but this is bigger in general. So it's not quite a TS TQFT, but so still quite interesting and I think not well developed. And we still have a reality, just from the construction, whenever you have F form or something more general, a cobordism from gamma 0 to gamma 1, given an element of the state space of gamma 0 can be represented by an object or a linear combination of objects with boundary gamma 0. So taking this object, composing with F, gives us an object with boundary gamma 1 and induces a map from the state space of gamma 0 to gamma 1. So we still get a functor. So for each cobordism, we can assign map of the state spaces. It's still a functor, but not quite TQFT in general. And particularly in the example we're discussing today, it's not known whether it's TQFT, whether there's such isomorphisms or gammas planar trivalent graphs. So some examples. Simplest example, when gamma is the empty graph. Well, it's an empty graph, and all you see is the closed form, which you can evaluate right away. And then you can check that in the quotient in the state space, a closed form is equal to just its value times the empty form with empty boundary. So here I distinguish between empty graph object and empty form object. This is empty form, this is empty graph. So the state space for the empty graph is just multiples of the empty form. In fact, when you're in this universal construction, if you have a closed component, you can just evaluate it and otherwise remove from the expression. Now, when graph gamma is a circle in the plane, you can check that the state space of gamma is three-dimensional over the state space of the empty graph. So the state space is given by this basis of a disk. So again, so we need, so we're saying that this state space, at first it's potential to be anything, any linear combinations of things that are bounded. But we can in fact reduce to just linear combination of these three forms, a disk with a dot, a disk with two dots, times any elements of R. So it's a free module of rank 3 over R. And you can think of this conceptually, you can think of ground ring R as the equivalent homology of a point for the group U3. So that's symmetric functions in three variables. And then you can think of the state space of the circle as the homology of CP2 equivariant under the action of U3. So this is 3 times as big as this. And so some of this has geometric interpretation using equivariant homology. And you prove this results by establishing various skein relations. I don't have much room here, but you can check that you establish a relation saying that you can cut. Everything is defined using columns. You can check that a cube like this can be cut into the sum of many terms with some various numbers of dots on them, because the evaluations using colorings give you the same number, no matter what's on the outside. So this helps to understand what's going on up to a point. If you have a graph gamma and you add this circle to it, you can check that the state space is 3 times the state space of gamma. You can write it as state space of gamma tensor R, tensor A over R. So tensor this space over this space. And you can also, another example. So if this is the graph gamma, this is the simplest graph with trivalent vertices. Then you can check what its state space. Its state space is really generated by this form, and you can put dots on those facets, and that sort of spans everything. You can identify the state space for this graph with the equivariant homology for the same group U3 of full flags in C3. So a 1 flag and a 2 flag in C3. Again, coefficients are here the working characteristic here, which allows us to capture more graphs. And then you can derive skein relations using skein relations on these forms. You can derive simplifications. You can derive the state space of a graph which contains this diagonal facet, a facet with 2 edges. It's just sum of 2 copies of a state space, but without that diagonal facet. So this simplifies the graph. You can check that the state space of a graph which contains triangle facet, triangle region is just isomorphic to this facet again through cobordisms. You can check what is that standard cobordism from this graph to this graph, which creates a singular vertex. You can check that this singular vertex, when viewed from this perspective, is an invertible cobordism. So this cobordism is reflection on mutually inverse maps. And you can also get a decomposition for a region, for a graph which contains a square region. So for those graphs, the state space is isomorphic to the sum of these two state spaces, again through canonical cobordisms between this graph and this graph. I should maybe mention, going back to this equation, that the maps back and forth will be given by cobordisms of this form, going from this graph to this graph and back. And we also need to put dots in strategic places to get this isomorphism. And now, in this setup, you'll eventually run into trouble because there'll be no simplification for a pentagonal region. So we don't know how to simplify things in this case. So very naive conjecture. The conjecture is that the state space of a planar trivial graph gamma is a free R module of rank the number of type colorings of gamma. So type colorings of gamma are colorings of edges. We color edges of gamma in 3 colors, such that at each vertex the colors are distinct. And that is proportional to the number of 4 colorings of the regions of gamma. So all of this relates to the 4-color theorem, and this relation goes back to Khovanov and Roska. We did things on the more combinatorial side. So this lecture, this kind of construction is borrowed from joint work with Lou, Adrien, and Robert from a couple of years ago. So I put some references here. So there's in this construction, there is sort of a quick increase in complexity once we get to graphs where each region has size at least 5. Then we don't have any scaling relations to simplify the state spaces of these graphs and inductively compute them. So we don't know, so in general, we don't know how to understand the state space of the graph gamma if gamma is the dodecahedral graph. So in this case, it's not known what the state space is. It's a graded module over ring R of symmetric functions and 3 variables. And so there are some bounds on the size of this module, but there is no answer is known as of today. So it's very quickly, complexity goes up. But there is one case that is relatively simple. And if you want to relation to link homology that's already been understood, then you can restrict to a case when the graph gamma is bipartite. So graph gamma is bipartite, so gamma is a trivial graph. So bipartite means that we can orient the edges so that at each vertex the edges are all in or all out. That's a bipartite graph. And you encounter these bipartite graphs if you're doing SL3 link invariant. So if you're doing Kuperberg bracket or Kuperberg SL3 link invariant, in Kuperberg bracket you start with a planar diagram of a link, and you simplify each crossing. Simplifies crossing. I might get powers of Q wrong, but that's something like Q squared. And then you have, so you're reducing diagram of them. You're using crossings to linear combinations of diagrams of planar graphs, trivial graphs, bipartite. And then Kuperberg has decomposition rules for simplifying those planar trivial graphs, the invariance assigned to them. And in fact, this goes back to, I think, mid or the 1990s. I referred to his paper on spiders for rank 2D algebras. And then at some point, there was a indication of his construction was found only for SL3, not for other rank 2D algebras. And in verification, his invariant becomes a graded rank of a homology theory for planar graphs. Cobordisms within these graphs give us maps. So these are forms. And to build in homology, you need to take us state space of one graph, state space of another graph, form the map between them given by the cobordism by suitable form, and take the cone of the homologies of these objects and iterate over all clusters. So it's sort of similar to the construction of SL2 in homology, except that you have to deal with more complicated objects in the middle, not just collections of circles, but Kuperberg webs for SL3. And the map between the state spaces of these graphs is given by suitable forms. You go from one graph to another graph through a form that's identity outside of this region and something standard like the singular saddle inside the region. So the map here is induced by this form. And so the form story for SL3 homology goes back maybe 15 years or so. The novelty here is that we can, this kind of close to boundary approach where we start with variations of closed forms and from them build homology, build the state spaces for tridimensional planar graphs. And another novelty is that we, in the story I told you today, we can have unoriented forms, unoriented graphs, and that's much harder, and that brings us closer to the four-color theorem. But just again, so if we restrict to bipartite gamma, then everything can be reduced, and we can prove when it's easier using the scaling relations from homology groups of bipartite planar graphs. It's you can easily show that the graded dimension of a state space of a bipartite graph is what we get out of Kuperberg's SL3 bracket. And then you can check that the homology of links you build this way calligraphies the Kuperberg SL3 quantum invariant. And so in the sphere, you kind of see homology of flag variety, homology of projective space CP2, homology of flag varieties in C3. And again, things can be said without bringing in this very general graphs. With general graphs, we get more mystery. So we don't know we don't know a formula for the dimension or rank of state space of an arbitrary graph that's not bipartite. So already the dihedral graph is a problem. And we don't know whether the state space of the disjoint union is appropriate tensor product of state spaces. So of course, if the state spaces ultimately end up not being projective modules, then the notion of tensor product is not clear, because should we take some kind of derived product or not, that's not clear either. So you quickly run into difficulty in the story as long as you bring in non-bipartite graphs and unoriented forms. But some of the motivation most of the motivation came from link homology. So there's an oriented version of this evaluation that works for LN, for GLN. This is the work of Robert and Wagner. And it's a more complicated evaluation where facets of the form can carry thickness. So facets can carry thickness A and B from 1 to n, such that facets of thickness A and B can merge into facets of thickness A plus B. And then the envelope of coloring is a little bit more complicated. So then you have a set of colors 1 through n. Let me call it I sub n. And then you color a facet of thickness A by I, where I is a subset of I sub n of cardinality A. And you call a facet of cardinality B by J in IN of cardinality B. And given this I and J, the facet into which they merge must be colored by I union J, disjoint union, So you kind of have the skulls floating from thinner facets into bigger facets. And the coloring is determined by what it does on the thinner facets. And then you can play a similar game. You can build for each color I, you can look at Fi of C, the union of facets whose coloring contains color I. And you can form Fij of C. Fij of C would be take surface Fi, surface Fj, take the symmetric difference. And so for instance, if you have I and I, J and J, then Fij of C will contain this facet, but not the thick facet. And then we have a similar formula which involves minus signs because over Z and variables, and that eventually gives rise to purely combinatorial approach to link homology for GLN. And so categorizing specializations of the complete PT polynomial, and variations of complete PT where lines of the link, components of the link are colored by exterior powers of the fundamental representation B. And so this is most algebraic, most combinatorial counterpart of the many constructions of GLN link homology using matrix factorizations, using coherent sheaves on Creo varieties, using proprietary categories. So there are many approaches. They should more or less all lead to the same or very similar homology groups. It has not all of them have been fully understood, but this approach using form variations is the most algebraic and combinatorial one, and it's unique because in some sense it's unique because you start with evaluations of these closed objects and then build and then use this as some kind of bootstrap to get to homology of cross sections, later to homology of link diagrams, etc. But it's based on these beautiful models where you take a closed form, take colorings of this form, build surfaces out of these colorings, and the evaluation knows in particular about further characteristics of those surfaces. So I think it's a really beautiful model of Robert and Wagner. There's definitely a lot of interest in seeing more of these models, because I don't think it's the only beautiful model in the story. But the question is, how do you find more beautiful models in there? That's not clear. So maybe that's a good time to stop and take questions. Thank you.
Oh, thanks very much, Mikhail. Are there questions? Just if you want to ask a question, just unmute yourself and ask.
So go ahead, Dale.
This idea of a foam reminds me of Matveyev's work on three manifolds, that if you take a closed three manifold and remove a small ball, then it has a spine, which is a foam in your definition. Is that correct?
It's definitely very similar in that for forms, we look at these W complexes with generic singularity. And it is very similar to special spines of three manifold. Very similar to spines of three manifold. So there's definitely strong analogies with the work of Matveyev and other people on special spines of three manifold. And there's also a question whether some of this can be, some fancy version of this can be useful for understanding CW complexes in dimension 2. They have simple homotopy equivalent. However, some kind of models like this can be useful for understanding anti-surface conjecture or similar problems about two-dimensional complexes. But I think this is kind of, this example, it's more targeted for forms embedded in free space. I don't think it's targeted. It's kind of good. I don't think that. I think we tend to deal with more general two-dimensional CW complexes, not embedded anywhere up to say simple homotopy equivalent one would mean something completely different, but maybe this could be a source of intuition.
Matveyev defined complexity of a three manifold using foams. I think it was basically the minimum number of singularities. Does your evaluation have any connection with that? You know, is one a lower bound for the other exponent or something like that?
Yeah, so it's a good question. I don't know how to use it for, as well as this can be related to complexity and problems for three manifolds. But again, this example, these variations are specifically for forms in R3. And we specifically, we want to have these variations and then we use them to build state spaces for planar graphs. We take a cross section, we see a planar graph, we build a state space, just call the form to the boundary, modular relations. And the relations come from the evaluation of forms. So there's a separate question if there's an interesting theory for evaluations of the forms embedded in modular three manifolds. Or, I mean, so there are just lots of questions. Or can we build three manifold invariants using this kind of taking special spline and then doing sort of similar coloring, kind of coloring of special spline, or if there's any similarity with quantum physics symbols and for zero invariants. So there are lots of good questions here. But so it's an interesting space-sum model for the generic post-fine type of standard CW complexes embedded in this space. But I think we just need to see more examples to see what it's going.
So to follow up on Dale's question, does the evaluation change under the 3-2 move for foams?
Well, I think if you do homotopy deformation of a complex into something else, is going to change.
Could you repeat that, please?
Yeah. So this is only for forms embedded in free space. So some of the material forms are not even cannot happen here. But some of the material forms cannot happen in free space.
Yeah, sure they can.
Well, yeah, but internally it's not invariant under. If you look at the moves that can happen, the variation is not invariant under the field.
Okay.
It's not have to be invariant.
And early on, you said that foams were sort of the generic situation. So if I had a, say, a finite group, and I just used the multiplication table for the trivalent vertices, then it looks like you have something related to representations of the knot group that's carried on the foam.
Well, so there might be more. One can look into building more examples of the variations using, for instance, solving by elements of a finite group, by a subset of elements of finite group. Because here we are sort of coloring by non-trivial elements of fine group.
Mm-hmm.
Or the sort of coloring passes by, well, as usual, only 4-color story, in the 4-color fitting story, the coloring
Right.
by non-zero elements of this Abelian group.
I see.
Because it's a good question to just find more interesting variations of this form, but we need coloring plus variation function. We need enough coloring and the variation function.
You talked about the pairing being non-degenerate, and I wonder if there's a zigzag identity that corresponds to your non-degeneracy condition.
Non-degenerate, well, this is just going to kill everything that's in the kernel of the Badinian form. So in this sense, it's very general. You can take any sort of n-dimensional object you like, manifold of declarations, not full of functions on closed objects. And then from this function, you can build a linear form on the space with a basis non-closed object. And you can mod out by the kernel of the form. But if the function is heavy generic, well, there's nothing in the kernel. But in some cases, the count would be very long. The function is very special.
Thank you very much.
Are there any other questions? Well, just remains for me to thank Mikhail very much. Very interesting talk. Thank you. I will end the meeting now, and I'll send around details of next week's talks very soon, plus a recording of this talk. Okay, bye for
And
now.
please remember to send us your slides.
Absolutely.
Yeah.